Hi and welcome to the next lesson in the subroutines series. This lesson is called Call and Ret. Objectives of this lesson. We will study the call and ret instructions. We will see examples of using call and ret. Then we will understand the stack's meaning with respect to function calls. Let's begin with an example. We have here a function that calculates the sum of a list of numbers, or to be more exact, D words. We have here a short description of this code. As input we get inside ECX the length of the list, and inside ESI the address of the list. As output we get inside EAX the sum of all the D words in the list. Let's take a fast look of how it works. We first zero EDX, and then we have this loop, which in every iteration loads one D word and adds this D word into EDX. Finally, we move the total result from EDX into EAX. Pretty simple. We want to use this code as a function. So we add those pushes in the beginning and pops in the end to make sure that we don't change the EDX and ECX registers. In this example, we do want to change EAX because this is how we deliver the output. But we don't want to change any other registers. We don't want to have any strange or unexpected side effects. So we just keep those registers to the stack and then we restore them from the stack. Basically, this code really does the same thing as the previous one, but the only difference is that this one doesn't change EDX and ECX. Here we see a new thing. We want to use this code that we have just written, some nums. We have already seen in the past a crude way to do it, but here we can see a new way. This is the way it is usually being done in the x86 architecture. We use two new instructions, call and ret. This is how those two instructions are usually being used. Here we want to call or to invoke the sumNums function. So basically this is how we do it. We first load ESI with some list. Here it is called myList. This is probably some list in memory, maybe in the data section or the BSS section. Next we load ECX with the length of the list, which represents the amount of D words in the list. This is just a constant. It is just a number. Finally, we call some nums. We haven't yet explained what exactly this instruction does, but let's just assume that it does what we want it to do. It just calls the function, which means that it takes us to this new location. Here we just execute the sumNums function, which we have already seen that it just adds all the D words in the list. And finally we have this instruction, ret. We still haven't defined exactly what this instruction does, but let's assume that it just takes us back to the correct location, which is here, the next instruction after call. Basically this is how it looks like. From the call we jump here to the sumNums label, then we execute this function, this sumNums function, and then we use the ret instruction to come back. This is a concept that we have already seen. Previously we used jump instruction to get this behavior, but here we have two special instructions, call and ret. Maybe in some other case we would like to use some nums for two different lists. In fact, usually this is what is going to happen, because if we have invested the time to write this piece of code as a function, the function SumNums, then we probably want to use it for more than one list or for more than one case. So in this example, we call this function SumNums twice for two different lists. By the way, I allowed myself to not write the full code of the function SumNums. So please assume that the code that we have seen previously is somewhere here. It just makes the code longer, and I want to concentrate on how Call and Ret works and not how the SumNums function works. Let's see what happens here. As opposed to the previous example, this time we do everything twice. We first load myList1 into ESI, and then list1 length into ECX, and finally we call SumNums, and we store the result inside EDX, probably for future use. Next we do the same for list number 2. We load myList2 into ESI, and then we load list2 length into ECX, and we call SumNums, which is going to calculate the sum. Then we keep the sum inside EBX, probably for future use. So in the end of this long piece of code, we have inside EDX the sum of list 1, and inside EBX the sum of list 2. But then comes the question, how come that Ret knows where to return? Basically, in the first call to SumNums, we call to the SumNums function, and then Ret returns to the next instruction here, move. In the second call, again we call the SumNums function, and the Ret returns, but this time it returns to a different location. Somehow magically Ret knows where to return. This time Ret returns to the next instruction after this call instruction. So it returns to this instruction, move EBX EAX. The big question here is, how can Ret know where to return? We already know that there is really no magic in anything in the computer. It is just about knowing how to organize your bytes. So let's try to understand what really happens here. We begin with understanding the call and the Ret instructions. The call instruction stands for call procedure. Procedure is just another name for function or subroutine. Basically, call does the following two things. First, it pushes the address of the next instruction to the stack. What do I mean by the next instruction? I mean the next instruction after the call instruction. So first, it pushes the address of the next instruction to the stack. And next, it jumps to the location arg. I remind you that call takes one argument. Jumping is equivalent to changing the value of EIP. I remind you that EIP stands for Extended Instruction Pointer, and it always points to the current instruction. Next, let's take a look at the Ret instruction. Ret stands for Return from Procedure. This instruction basically does two things. First, it pops a dword X from the stack, and then it jumps to location X. Or maybe in different words, it sets EIP to have the value X. So, we can conclude from what we have seen about the description of Call and Ret that the return address is kept on the stack. So, this is the secret of the Ret instruction. This is the secret of how the Ret knows where to return. It is very simple. The call kept the return location on the stack. So whenever we get to the Ret instruction, we just pop the return address from the stack and we know where to return.